Good evening, everyone. I'm highly excited to welcome you on this platform today. Being the last facilitation session for CHM204. Today, by God's grace, we are going to be looking at the week 8, topic 8 of our facilitation, which is actually the end also of the facilitation for this semester. My name still remains the same, Professor Lainka Jani, your facilitator for this course. Thank you very much and be blessed, and you are welcome on board for today's class. Today we are going to be ending up, as I earlier said, with the Unit 2, the remaining part of Unit 2 of Module 3, where we have been dealing with the secondary and higher main group elements. And today we are going to be looking at Group 17 and Group 18. At the end of the topic, the learner should be able to, number one, know and classify the elements included in Group 17 and 18. They should be able to understand the electronic configurations and write them perfectly for this Group 17 and 18. We should know the reaction involving Group 17 and 18, and we should know the application or general use of some of the elements of this group. The Group 17, sorry, that heading should be Group 17 elements. The Group 17 elements, the first of it is fluorine. And when you want to note how they appear, in the second period of that Group 17, we have the fluorine. In the third period of it, we have the chlorine. In the fourth period, we have the bromine. In the fifth period, we have the iodine. The sixth period, we have the astatine. And then chlorine was actually the first among all these elements of Group 17 to be discovered. The general name of the Group 17 are actually halogens. Chlorine was first to be discovered, and it was discovered specifically in 1774, followed by the iodine, followed by the bromine, followed by the fluorine. Astatine was the last to be discovered. It was discovered in the 19th century at 1940. Why are they called halogens? The word halogen is actually derived from two Greek words, which is the al, which means salt, and the gene, which means form. So in the summary of it, halogens can be referred to as the salt former. And that's the reason why they have one of the highest noted reaction with the main group elements of at least the metallic part to form the most ionic salt compound that have perfect solubility in water at all time. Together, having said the reference fact that the halogen form the salt when they react with metals. So halite is the mineral name for rock salt. So a natural mineral consisting essentially of sodium chloride. So sodium chloride, which is the table salt, there's a natural raw material, the natural mineral that has it in large quantity in the rock salt form, and we call it halite there. They are also in our daily life, whether it be the fluoride that goes into the toothpaste to strengthen the bone, the gums, and to make the teeth strong. You know, the fluoride and calcium GP is good to give strong power to the teeth. The chlorine is used as disinfectant in the treatment of water. It's even having a better disinfecting activity and ability than the ozone. We use iodine every day because iodine protects against the goiter, the inflammation of the thyroid hormones to give the goiter at the thyroid gland region. When we have somebody that have goiter, is lack of iodine. And that's the reason why iodine is put in a common material that is cheap to afford for every household, which is part of the reason why the food chemistry research has regulated by NAFDAC as condition that all the salt form used for cooking must be doped with the iodine, so that as people are using salt for their cooking, they are indirectly consuming iodine, and that has actually removed a lot of the problem of goiter in this 21st century. Property of halogens. Halogens are toxic non-metal located on the left-hand side of the noble gas. They are actually the class that preceded the noble gas, because the noble gas is the last class on the main group elements. Astatine, which is the last member of this group 7, is highly radioactive. And its inclusion in group 17 is actually based on the similarity of its behavior to iodine. Otherwise, astatine is so radioactive with the short half-life that it's difficult to put him under that group. But because of his behavior with iodine, which is directly the element on top of him in that group 17, is still included as part of group 17. They are more reactive than other non-metals. They are the most reactive non-metal, and their reactivity goes downward because fluorine is the first member. Apart from having small size, it has the highest electronegativity in the whole of the periodic table. So it will be the one that will accept the electron, have the fastest rate of accepting electron from the metal to form compound. And therefore, we said, fluorine will be much more reactive than chlorine. Chlorine will be much more reactive than bromine. Bromine will be much more reactive than iodine. So reactivity decreases as you go down the group 17. So we can really say that if fluorine is the most reactive in group 17, then astatine is the least reactive. Halogen form diatomic molecules. They don't exist as monoatomic molecule. So when you are talking about chlorine, chlorine can only be dealt with as an entity, as a chlorine gas, which is Cl2, iodine gas, I2, bromine gas, and then fluorine gas. They are diatomic in nature. And the bond of these diatomic molecules are non-polar covalent single bond. They combine with most elements, but they are never seen in an uncombined state in nature. All halogen form group one salt with similar property. That means when fluorine is treated with group 1, sodium chloride, sodium bromide, all of them have ionic nature, and they have similar property. Many chemical reactions that involve halogen are redox in aqueous solution. Let's pick the first one, fluorine. Fluorine is a diatomic molecule and is the most abundant halogen in the earth's crust. Fluorine is a pale yellow gas at room temperature and the most electronegative element. We have said that. It has small atomic radius with oxidation state of -1, except in its elemental diatomic. The only time you cannot see full fluorine as having -1 is when it's in elemental form. And you know that that form is F2, which has oxidation state of 0. Fluorine is extremely reactive with all elements, except with non-reactive group 18, which are called the noble gas. But when we get to noble gas, you can see some special exemption again. In water solution, hydrofluoric acid is a weak acid. Although fluorine is highly electronegative, its electronegativity does not determine its acidity. Why? Because of its peculiar nature as the first element in that group 7, with the second period phenomenon, with a small atomic radius, with its small size. So HF is a weak acid due to the fact that the fluoride ion is basic with pH greater than 7. Fluorine produced very powerful oxidants. For example, fluorine can react with the noble guard in an exceptional cases, especially with xenon, to form strong oxidizing agent, which is xenon difluoride. Chlorine. There are so many functions of fluorine. They are in your material, so you can get as many as you want there. Apart from being used in the toothpaste to provide strong bone and protected gum. Its atomic number, chlorine as elements in group 17, is in period 3 of that group 17 with atomic number of 17. It's one of the most commonest elements in group 17. It forms the atomic molecule just like the fluorine, but it has oxidation state of -1, +1, 3, 5, and 7. This is because it now has a low line d orbital that is ready to receive electron if there is an excitation of electron. But if you look at fluorine, fluorine does not have energetically available d orbital. Therefore, fluorine cannot expand beyond the octet in its compound forms. But chlorine can do that. That's why chlorine is able to come in various oxidation states. You see, you can have PCl3, you can have PCl5, you can have POCl, you can have POCl3, you can have NaCl. So a lot of things having various oxidation states. So at room temperature, it appears as light green gas. Since chlorine bond is weak, that make it the atomic molecule, then chlorine molecule is very reactive. Because the weakness of the bond shows that it can break easily to attack other things, and that's what confers reactivity. Ability to live where you are, to attack where you are not, to transform things is called reaction. You see the groups 18 are non-reactive. We call them inert gas because they already satisfy the octet rule, which is what every element is tending to satisfy. And some satisfy it by losing the electron. We call them the metal. Some satisfy it by gaining the electron. We call them the non-metal. And when they lose and gain, it forms cations for the metal and anion for the non-metal. But for the chlorine-chlorine bond, the reactivity is so high because that bond is so weak. And that's the reason why you can have easy halogenation of alkane, when alkane is supposed to be called paraffin because they are not reactive or they have little affinity. But we know they cannot undergo a lot of reactions, but specifically they will undergo substitution reaction with halogens in the presence of peroxide or in the presence of photocatalyst or UV light. So chlorine reacts with metal to produce salt, and we know one of the strongest salt compound that could be formed is from this salt compound with main group. Some of them, the solid form salt, can have as high as melting point of 800 degrees centigrade, which is 8 times the boiling point of water, because of that strength that comes as a result of the ionic bond formation between the main group metals and the chloride or the halides. Chloride ion, which is cation, are most abundant ion that dissolve in the oceans. That's why you have a lot of salt water, you can get a lot of chlorine from them. Chlorine exists in 2 isotopic form, and we know what isotopic means. Isotopic is the occurrence of one element in more than one that exists in more than one atomic mass state. When that happens, you have isotopy. So there are 2 isotopes of chlorine. We have chlorine 17 with atomic mass of 35. We have chlorine 17 with atomic mass of 37. And when you calculate the overall relative abundance, you are able to come up to have the molecular or atomic weight of chlorine being 35.5. Sodium chloride is most prevalent compound of all the chlorides. You can read from the material various usefulness of chlorine. Chlorine is number one thing you use in the disinfectant and water treatment. We use chlorine a lot in the formation of various sorts of the main group elements that are metals in nature. We use chlorine in bleaching and removing the color impurity from industrial processes. So many things we use the chlorine for. That leads us to the bromine. Bromine is a diatomic molecule, just like generally we have said about all the halogens. At room temperature, bromine actually is reddish brown liquid. Its oxidation state varies from -1 to +1 to 3 to 4 to 5. Of course, because of the available d orbital expanded object is available, is possible. But you see, in all this one we have been saying, there is number one thing that is very paramount to them, and that's -1 oxidation state. Because all of them have 7 electrons in the outermost shell, it is easier for them to gain one more to become -1 than to lose the whole of 7 to become +7. That's why number one oxidation state of them is -1. But as we are going down the group towards the last element, this thing begins to reduce as a result of effective nuclear charge, which you remember we have discussed that when we are looking at some other higher group elements. Bromine is more reactive than iodine, but not as reactive as chlorine. So bromine also has 2 isotopes, bromine 79 and bromine 81. It consists of bromide salts, which have been found in the sea. World production of bromine has increased significantly over the year. Why? This is because of its access and the longer existence. Accessibility and the longer existence makes it to be of high significantly increasing their production lately. Like all of the other halogens, bromine is also a good oxidizing agent, and it is very toxic. The other two groups are the iodine and the astatine. Iodine exists as a diatomic molecule. It has oxidation state of -1, 1, 5, and 7. At room temperature, iodine is a violent solid with a stable isotope of iodine 127 and can be easily isolated from the sea water. Iodine is not very soluble in water. The solubility may increase if the particular iodide are mixed. It's used in treatment of thyroid hormone production. Astatine is a radioactive element with an atomic number of 85 and the symbol 80. It has the oxidation state of -1, +1, 3, 5, and 7. It is the only non-diatomic halogen. See, all of the halogens are diatomic in nature, but astatine exists as a monoatomic element. Why? Remember, the metallic character is increasing as you go down the group. That when you get to astatine, it's as if it's metal. It's as if it's a radioactive species, and that gives him the credit to stand as a monoatomic, just like the same way sodium will have stand. The same way sodium will have stood as a monoatomic. So this one can also stand as monoatomic because it doesn't need to form a covalent bond as a result of what it is. Astatine appears as a black metallic solid at room temperature. Astatine is a very rare element, so has little information on its activity. Astatine has a very short radioactive life, no longer than a couple of hours. It is very important that we must know how to write the electronic configuration of each of these elements. We have been saying it that the first thing you must learn in every main group element is their electronic configuration. The electronic configuration is as seen here, that of fluorine 1s2, 2s2, and 2p5. And it shows that it has atomic number of 9. The first shell having 2 electrons, the second shell having 7 electrons, out of which 2 is in s orbital and 5 is in p orbital. periodic trend for the halogens. Melting point is one of the scar property. How does this go? As you go down the group, the melting point increases. The same way as you go down the group 17, the boiling point increases. And why? Because as you are going more down, there is a tougher strength. We said, like I'm starting now, is so strong that it exists as a monoatomic element. So to break it down, high thermal energy is required before it can transform from a phase to another, from solid to liquid or anything. That's why we are saying, how does the boiling and the melting point vary down the group 17? As you go down the group 17, these things are increasing. Covalent radius, we have defined all these things. It increases down the group 17. Ionic radius, it increases down the group 17. But first ionization energy, which is energy required to take the first electron in the atom shell at the gaseous state out of the system. How does that vary? Fluorine, because its electron in the atom shell is so close to the nucleus inside. So we say that the attraction from the nucleus, which has the positively charged particle called the proton, to that electron of fluorine is so strong. And therefore, it will not be easy for you to pull off the first electron in the atom shell of fluorine. So fluorine, we have the highest first ionization energy. But as you are going down the group 17, you discover that that thing will be reducing. Why? Because the highest or the last electron in the atom shell, as you are going down the group, will be farther away from the nucleus of the atom where the proton is. So there will not be much attraction. And therefore, the electrostatic force of attraction that should have existed is being broken down. So you are easily pulling off the last electron in the atom shell. So that's why fluorine has the highest first ionization energy, 1,781. And they are starting as the lowest first ionization energy, which is 890. What about the electron affinity? What about electronegativity? Electronegativity and electron affinity, they behave alike, but electron affinity is in form of energy, while electronegativity is in form of a phenomenon. The tendency of an atom to want to withdraw the electron density towards himself is called electronegativity. And therefore, fluorine has the highest electronegativity in the periodic table, which is 4.0. But as you are going down to chlorine, to bromine, the electronegativity will be reducing. So the same way we're talking about electron affinity, the love of something for electron, something that have high electronegativity, we have a strong love to want to accept electron to itself. Because fluorine is the one that have the highest electronegativity, so the love for the electron will be high for it and therefore require a lower energy. Hydrogen halide and halogen oxoacid. These are two major, apart from all the general reactions that we have cut across when we are dealing with other group metal when they are treated on halogen. So we are saying what are the other specific things that halogen can form. We have the hydrogen halide and we have halogen oxoacid. An halide is formed when an halogen reacts with a less electronegative element to form a binary compound. Example is formation of hydrogen fluoride, hydrogen chloride, hydrogen bromide. You see, when an halide is reacting with a less electronegative, hydrogen is less electronegative than fluorine. So in the gaseous state, when hydrogen reacts with fluorine, you are going to be getting a gas called hydrogen fluoride. The same thing with chlorine, you are going to be getting hydrogen chloride. But what is the second group is the halogen oxoacid. What is an halogen oxoacid? Halogen oxoacid can be defined as an acid which have hydrogen, oxygen, and an halogen atom. It may be more than one, it may be one, but it must necessarily have hydrogen, oxygen, and halogen. That's why we call them oxoacid. The acidity is determined through analysis of compound structure. Example of such is what we have as HOCl. You know, HCl is hydrogen chloride. Immediately the oxygen is fixed in, it becomes oxoacid. HOCl is H plus and OCl minus 1. That's why it's able to form HOCl. And HOCl has name of hypochlorous acid. HClO2 has what is called the name chlorous acid. HClO3, as that oxygen is increasing, the strength is increasing, and that is called chloric acid. HClO3 is chloric acid, HClO4 is perchloric acid, and HOBr is hypobromous acid. Just like you have a hypochlorous acid, you can have hypobromous acid. If you have HOI, that's hypohalous acid. All these ones that are acid, you know, natural mineral acid are supposed to be hydrogen being the only electropositive there, like HCl, like HBr, and all those. But immediately oxygen is coming in, you have oxoacid, halogen oxoacid. State of matter at room temperature. The color of halogen is a consequence of the absorption of visible light by the molecule, which actually causes electronic excitation. When you are promoting electron from the lower state to a higher state, you are exciting that electron. And the excitation of that electron will require an energy before it can have enough strength to be able to move from one lower phase to a higher phase. And therefore, the energy is quantized in such movement. And this is what leads to the phenomenon of what we call absorption. But if something is at the excited state and you have to relax back by falling back to the ground state, that's what is called the emission. So the state of matter at room temperature can actually put a lot of understanding to what the color of these elements are at room temperature. So the fluorine absorbs violet light and therefore appears light yellow. Iodine absorbs, remember when you are talking about color chemistry, absorption and reflection. Whatsoever the color of the light that is absorbed is what will determine the color that it will reflect. And the color that will reflect is now what is the color that we see it having physically by the physical eyes of observer. So the iodine absorbs yellow light, therefore it appears as violet. And we should remember that yellow and violet are complementary colors. Generally, the color grows darker as you go down the group 17. See fluorine, pale yellow. See chlorine, pale green. See bromine, red brown, becoming deep. See iodine, violet, and see astatine, black and metallic. The importance of inorganic compounds of fluorine, just as an example. There are some other inorganic elements combining with fluorine to get a lot of things which are useful in day-to-day activity. So the first compound there you see is used in the manufacture of aluminum. Boron trichloride is used as catalyst, and you can see other examples and what they are being used for. And that leads us to the group 18, which are called the noble gas. Group 18, which are called the noble gas. The noble gas, which are the group 18, are allocated in the far right of the periodic table. They actually constitute the last column to the far right of our periodic table. They were previously referred to as inert gases. Why? This is due to the fact that their filled valence shell octets make them extremely non-reactive. Because you remember when we started with this main group element, we said every element tends to want to obey the octet rule, apart from the first element of helium and hydrogen that we be looking towards the duplex rule. But anyone that is already in the second period in the periodic table, they actually want to obey the octet rule. So anything they have away from the 8 system in the atable shell is what tells us what they have naturally. If they have 8 electrons and they have 1 more electron outside, that 1 electron is disturbing them. They want to give it out. That's why we are saying sodium with atomic number of 11, 281, already have 8 maintained octets. So we want to give away 1. That's why it's +1 oxidation state, and that's why it's in group 1. So, but immediately we come to the group 8 now. They already have the 8, which every other element is hungry or fighting or working hard to attain. And in working hard to attain, some people will have to drop off excess on them, and they become positively charged, which are called cation, derived from what are called metals. In that taxon, have 1 or 2 or 3 needed to add to whatever they have to get to that height. And when they get that accepted, they become negatively charged, they are anion, and they are formed from the non-metal. But now looking at the group 18, they already have that 8 electron. They are not willing to give out electron to become a cation from the metal, and they are not willing to accept electron to become an anion from the non-metal. So they are a class of their own. That's why we call them inert gas. Make them extremely non-reactive. Noble gas are odorless, colorless, non-flammable, and monotonic gas that have low or no reactivity. Chemical properties of noble gas. It is very important at this junction that the students should know all the noble gas according to their order, because if you know them, it will save you of a lot of headache on trying to cram anything to write the electronic configurations of all other main group elements. Because immediately you know the noble gas that preceded that main group, just put that noble gas in a square bracket and complete it with the number of electrons afterward. So we have the noble gas in the order helium, neon, argon, krypton, xenon, and radon. The atomic number of them are seen here, and their electronic filling of their shell or orbital is as seen in that column 3. But that last column is their electronic configuration, which it is important for us to note. And when you look at it very well, you discover that the noble gas, there's one peculiar thing about the noble gas, which you must take note, is that when you look at neon, when the principal quantum number is 2, it's saying in the second shell, you have total of 8 electrons already. 2 plus 6 is equals to 8. When you come to the argon, in the third shell, we have 2 plus 6, 8 already. You look at the krypton in the fourth shell, you have 2 plus 6, 8 already. You look at that of the xenon in the fifth shell, 2 plus 6 is equals to 8. And that of the radon in the sixth shell is 2 plus 6, making 8. So it should not be difficult for us to be able to write the electronic configuration for this noble gas. We have said that noble gas are not reactive, but after thorough research effort of some scientists, it was discovered that there are some noble gas that have some exception. They have some reaction, not they form compound not by physical reaction, They form compound by caging some other element into themselves or by using the lone pair to interact with some. They may not be too much stable compound, but they are compound that really exist. And that's why we are going to be looking at 3 exceptions. We're going to be looking at exception with example of each one of them. The xenon fluoride is the first exception. All the noble gas are non-reactive, but the fluorides of xenon has been found in nature. And there are 2 major classes of this. We have xenon difluoride and xenon tetrafluoride. And that xenon difluoride, what are the properties of this xenon difluoride? We have dense white crystalline solid. Xenon difluoride is very powerful fluorinating agent. They form covalent inorganic fluoride. They are very stable xenon compound. It decomposes on contact with light or water vapor. It has a linear geometry. The structure is linear. And if you want to see that, you remember when we are talking about the hybridization, when you say xenon difluoride, actually it exists in a dimeric form for better stability to confer on it. You remember that the Wesel length of the central atom, which is xenon here, will be 8, and it has 2 neighboring fluorine to join with him, and that leads to 10 bond, 10 electron, which is equals to 5 electron pair. However, xenon is bonding linearly with 2 fluorine with bond angle of 180 degrees. And what does that mean? That means that this is a bond pair between fluorine and xenon. This is a bond pair between fluorine and xenon. And fluorine xenon in this XCF2 are to have 5 pair. 2 of them are bond pair. Therefore, the 3 of them will be lone pair. And lone pair must be arranged in such a way to minimize repulsion. So there's a lone pair of electron here, there's a lone pair of electron here, and there's a lone pair of electron here. That's why the structure of xenon difluoride is as seen in the region below. And when we are looking at the second class of fluoride of xenon, we have xenon tetrafluoride. The creations of this xenon tetrafluoride was announced by Argoni in 1963. It was actually the first simple compound of xenon that was discovered. It was surprising because it's supposed to be a noble gas that was widely thought to be chemically non-reactive. That was the reason why the discovery was in the 19th century. Despite the fact that a lot of main group elements have been, phenomena have been discovered in the centuries before. For a long time, they never believed that xenon can form any compound because it belongs to the noble gas. But it is now widely accepted because these compounds have been characterized and been confirmed to be true. It's a colorless crystalline compound. It has a square planar molecular geometry, as you can see underneath there. The third example of the first exception, which is the xenon fluoride, is the xenon hexafluoride. Xenon hexafluoride, XeF3, XeF6, sorry. And this compound, to just look at some of its peculiar nature, is the strongest fluorinating agent. It's a colorless solid. It has the highest coordination of the 3 binary fluoride of xenium. And what do we mean by that? If you look at the disproportionation, we are seeing XCF2 combining with XCF4, and that leads to the 6. So, but the xenon there is the central, wherein you are able to relate the 4 and 2 fluorine to form 6 fluorine. So they have the highest coordination as a binary compounds. The formation is hexagonal and the compound is stable even at room temperature. It readily sublimes into intense yellow vapor. The structure lacks the perfect octahedral symmetry. Then the second class of exception are the xenon oxide. Xenon as a noble gas was established to have been able to form a compound called xenon tetroxide. Xenon tetroxide. And the structure is as seen above. Xenon tetroxide. And the structure is as seen. Xenon tetroxide, yellow crystalline solid. It's a yellow crystalline solid. It's relatively stable. Oxygen is the only element that can bring xenon up to its highest oxidation state. You can see this is 1, 2, 3, 4, 5, 6, 7, 8. 2 other short-lived xenon compound, apart from xenon tetroxide, have also been identified in nature. And that is XeO2F4, XeO3F2. And they are produced in the reaction of xenon tetroxide with xenon hexafluoride. So it means additional reaction of xenon tetroxide we have up here with xenon hexafluoride is what leads to disproportionation reaction to produce these 2 other groups. And when you see it carefully, you see that the 6 fluorine is disproportionated itself into 4 fluorine for the second and 2 fluorine for the first. So the second exception are the xenon oxide. The third exception are the radon compound. Remember, radon is the last group 8 elements, group 18 elements, the noble gas. So radon difluoride is one of the few reported compounds of radon. Radon reacts readily with fluorine to form a solid compound, but this decomposed on attempted vaporization, and its exact composition has not been ascertained. The usefulness of radon compound is limited because of the noble gas radioactivity. It's a noble gas at the same time, because it's the last in the group, it also have tendency of radioactivity. You remember that when you go down every group, the last element of that down every group always have one radioactivity phenomenon or the other. So radon not an exception, despite the fact that it belongs to inert gas. It also have tendency of some little radioactivity. That's why we call it noble gas radioactivity. The surprise, what is possible and has been established to be true. The longest lived isotope, radium-222, has a half-life of only 3.82 days. See how violent its radioactivity is. Radon emanates actually from the ground and is the biggest source of natural background radiation. Natural background radiation. That's why when you talk about radon, you type it to radioactivity. High concentration of radon can build up in cellars and basements. The ceilings of the building, that's the cellars, and the basement, posing at health risk. Another thing is that radon is estimated by the EPA to be the main cause of lung cancer among non-smokers. Activity. Why does fluoride always have an oxidation state of -1? That's the first one. Then I test that now. Remember that we also have that second period phenomenon, being the first element in group 17, having small atomic radius, small particle size, and then the tendency to hungrily receive one electron to make a 7-atomous electron to be objectful. Look at the periodic table. Explain how the following parameters vary down the group 17 element: ionization energy, and then electron affinity. Ionization energy, of course, when you are talking about that in group 17, as you are coming down, 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 what is expected of ionization energy, especially the first ionization energy, which is the energy required to take away the first electron loosely bound to the atomos shell of your group 17, is that as you go downward, ionization energies is expected to be reducing. Fluorine will have the highest ionization energy because its atomos electron is close to the nucleus of the atom, which has the positive charge. So there is an electrostatic interaction between those electrons and the central of the nucleus, strongly bound and influenced. So the energy needed to pull away one valence electron will be very high. But as we are coming to chlorine and to bromine, the shell is increasing. Therefore, where the atomos electron is located to the nucleus of positive charge of proton is far away. So it's not feeling the electrostatic attraction again to the center, so it can easily be removed with a little energy. What are halogen oxoacid? Halogen oxoacid, we have said that they are compounds of acid that have hydrogen, halogen, and oxygen embedded within. So if I have to give an example of that, you already know hypochlorous acid is there. You have HOCl, we have HClO2, we have HClO3, we have HClO4, we have HOBr, hypobromous acid. Noble gas, question number 4. Noble gas are meant to be inert. However, there are some exceptions. Provide name and molecular formula of 2 fluoride of xenon that are available or that occur in nature. So that one should not be difficulty. We just ended talking about that a moment ago. So today we have been able to deal with the last topic in our facilitation, which I believe we have prepared ourselves fully for the forthcoming exam. All the live facilitation we have done, if you have missed any one of them, they are on record. And we have actually put the link on the course page of this course. When you go to the course page of this course online, you can go through this subheading called Facilitation Session Recorded. When you click on that facilitation session recorded, you will see the 8 weeks of the facilitation we have done. And in each of the week, you will see the link to the recorded live class of that week. So take it together with your course material and go through it to listen to it over and over again. It will guide you in a lot of things and give more clarity to where you have challenges. However, I will also be available for you, as I've set the chat room on the course page, that if you have any question, you can write mail to me, you can call me on phone, or if you want to wait till Saturday, by Saturday 5 in the evening, be there to see if there are any students that need help or that need assistance or that want us to discuss further things that he thinks is not clear to him. So today, specifically, in conclusion, we have been able to, number one, know and classify the elements in group 17 and 18. We call the group 17 the halogens, and we call the group 18 the noble gas. And we said the group 17 has their elements in this order. The first one is the fluorine, followed by the chlorine, followed by the bromine, followed by the iodine, and followed by the astatine. And we said astatine is almost purely metallic because of the position it occupied, and it has high radioactivity. And we have also talked about the fact that we need to know the usefulness and the application of each of these group 17 elements, because all of them find relevant application in our daily life. We also talked about group 18, that they are actually called inert gas in the present state, in the earlier state of their discovery, because they have already obeyed the octet rule, not willing to give, not willing to accept. And that's why anyone that is not ready to give and not willing to accept will not form, will not undergo reaction and cannot form a compound. But it was discovered later that no, there are some exceptions. Xenon, for example, has some exemption in the sense that it has been discovered that there are some compound of xenon in nature with halide and the compound of xenon in nature with oxygen. And we gave example of the first set as the exception, or exception number one. We said we have xenon difluoride, we have xenon hexafluoride, and then we also talk about that of oxygen. Xenon tetroxide. We talked also that last day on the third one, which is radon. Radon compound has also been noted. But we said the radon is radioactive in nature, it is carcinogenic, and it should be treated with extreme carefulness to protect life and property. And we have also talked about the need to know how to write the electronic configuration for each of the elements of group 17 and group 18. You should be able to know some of the reactions. Group 17, they undergo, they gave us halogen oxoacid, they gave us the compounds of the halide, which are the hydride of the group 17. And we said those one in negation form will form their gas. But when we bubble this into aqueous medium of water, it forms the solution. So hydrogen reacts with the chlorine to form hydrogen chloride, but that passed into aqueous solution will become the hydrochloric acid. Though having the same molecular formula of HCl, but their states is not the same. Hydrogen chloride is in gaseous form, while hydrochloric acid is in liquid form. I've also been able to know that all these group 17 and 18 has their special application, and the student is expected to understand, know them, and be able to give example of such application. So on that note, we have come to the end of facilitation for this. We have come to the end of the facilitation for this semester. Thank you very much, and God bless. Please remember to check for the recorded live classes, to watch it, to hear it over and over again. And each of the courses for each of the topics, I've broken them into the PowerPoint for each session, and I call it specifically the instructional material for each of the topics. You can go through those ones in addition to your course material. Thank you so much, and God bless you all. Good night, and bye for now.